In quantum mechanics, the uncertainty principle, also known as Heisenberg's uncertainty principle, is any of a variety of mathematical inequalities asserting a fundamental limit to the accuracy with which the values for certain pairs of physical quantities of a particle, such as position, x, and momentum, p, can be predicted from initial conditions. Such variable pairs are known as complementary variables or canonically conjugate variables, and, depending on interpretation, the uncertainty principle limits to what extent such conjugate properties maintain their approximate meaning, as the mathematical framework of quantum physics does not support the notion of simultaneously well-defined conjugate properties expressed by a single value. The uncertainty principle implies that it is in general not possible to predict the value of a quantity with arbitrary certainty, even if all initial conditions are specified. Introduced first in 1927 by the German physicist Werner Heisenberg, the uncertainty principle states that the more precisely the position of some particle is determined, the less precisely its momentum can be predicted from initial conditions, and vice versa. In the published 1927 paper, Heisenberg originally concluded that the uncertainty principle was delta p delta q h using the full Planck constant. The formal inequality relating the standard deviation of position sigma x and the standard deviation of momentum sigma p was derived by Earl Hesse Kennard later that year and by Hermann Weyl in 1928. Sigma x sigma p greater than or equal to h/2, where h is the reduced Planck constant, h/2 pi. Historically, the uncertainty principle has been confused with a related effect in physics, called the observer effect, which notes that measurements of certain systems cannot be made without affecting the system, that is, without changing something in a system. Heisenberg utilized such an observer effect at the quantum level as a physical explanation of quantum uncertainty. It has since become clearer, however, that the uncertainty principle is inherent in the properties of all wave-like systems, and that it arises in quantum mechanics simply due to the matter-wave nature of all quantum objects. Thus, the uncertainty principle actually states a fundamental property of quantum systems, and is not a statement about the observational success of current technology. Indeed, the uncertainty principle has its roots in how we apply calculus to write the basic equations of mechanics. It must be emphasized that measurement does not mean only a process in which a physicist observer takes part, but rather any interaction between classical and quantum objects regardless of any observer. Since the uncertainty principle is such a basic result in quantum mechanics, typical experiments in quantum mechanics routinely observe aspects of it. Certain experiments, however, may deliberately test a particular form of the uncertainty principle as part of their main research program. These include, for example, tests of number, phase uncertainty relations in superconducting or quantum optics systems. Applications dependent on the uncertainty principle for their operation include extremely low-noise technology, such as that required in gravitational wave interferometers. It is vital to illustrate how the principle applies to relatively intelligible physical situations, since it is indiscernible on the macroscopic scales that humans experience. Two alternative frameworks for quantum physics offer different explanations for the uncertainty principle. The wave mechanics picture of the uncertainty principle is more visually intuitive, but the more abstract matrix mechanics picture formulates it in a way that generalizes more easily mathematically. In wave mechanics, the uncertainty relation between position and momentum arises because the expressions of the wave function in the two corresponding orthonormal bases in Hilbert space are Fourier transforms of one another, i.e., position and momentum are conjugate variables. A non-zero function and its Fourier transform cannot both be sharply localized at the same time. A similar trade-off between the variances of Fourier conjugates arises in all systems underlain by Fourier analysis. For example, in sound waves, a pure tone is a sharp spike at a single frequency, while its Fourier transform gives the shape of the sound wave in the time domain, which is a completely delocalized sine wave. In quantum mechanics, the two key points are that the position of the particle takes the form of a matter wave, and momentum is its Fourier conjugate, assured by the de Broglie relation P equals hk, where k is the wave number. In matrix mechanics, the mathematical formulation of quantum mechanics, Any pair of non-commuting self-adjoint operators representing observables are subject to similar uncertainty limits. An eigenstate of an observable represents the state of the wave function for a certain measurement value, the eigenvalue. For example, if a measurement of an observable A is performed, then the system is in a particular eigenstate psi of that observable. However, the particular eigenstate of the observable A need not be an eigenstate of another observable B. If so, then it does not have a unique associated measurement for it, as the system is not in an eigenstate of that observable. According to the de Broglie hypothesis, every object in the universe is a wave, i.e., a situation which gives rise to this phenomenon. The position of the particle is described by a wave function. The time-independent wave function of a single-moded plane wave of wave number k0 or momentum p0 should be interpreted as a probability density amplitude function. I, in the case of the single-moded plane wave, is a uniform distribution. In other words, the particle position is extremely uncertain in the sense that it could be essentially anywhere along the wave packet. On the other hand, consider a wave function that is a sum of many waves. With the addition of many plane waves, the wave packet can become more localized. We may take this a step further to the continuum limit, where the wave function is an integral over all possible modes, that is called the wave function in momentum space. Adding together all of these plane waves comes at a cost, namely the momentum has become less precise, having become a mixture of waves of many different momenta. One way to quantify the precision of the position and momentum is the standard deviation sigma. Since psi x caret 2 is a probability density function for position, we calculate its standard deviation. The precision of the position is improved, i.e. reduced sigma x, by using many plane waves, thereby weakening the precision of the momentum, i.e. increased sigma p. Another way of stating this is that sigma x and sigma p have an inverse relationship or are at least bounded from below. This is the uncertainty principle, the exact limit of which is the Kennard bound. This implies that no quantum state can simultaneously be both a position and a momentum eigenstate. When a state is measured, it is projected onto an eigenstate in the basis of the relevant observable. For example, if a particle's position is measured, then the state amounts to a position eigenstate. This means that the state is not a momentum eigenstate, however, but rather it can be represented as a sum of multiple momentum basis eigenstates. In other words, the momentum must be less precise. This precision may be quantified by standard deviations, in quantum metrology, and especially interferometry. The Heisenberg limit is the optimal rate at which the accuracy of a measurement can scale with the energy used in the measurement. Typically, this is the measurement of a phase, applied to one arm of a beam splitter, and the energy is given by the number of photons used in an interferometer. Although some claim to have broken the Heisenberg limit, this reflects disagreement on the definition of the scaling resource. Suitably defined, the Heisenberg limit is a consequence of the basic principles of quantum mechanics and cannot be beaten, although the weak Heisenberg limit can be beaten. In 1945, L.I. Mandelstam and I.E. Tam derived a non-relativistic time-energy uncertainty relation, as follows. An informal, heuristic meaning of the principle is the following: a state that only exists for a short time cannot have a definite energy. To have a definite energy, the frequency of the state must be defined accurately, and this requires the state to hang around for many cycles, the reciprocal of the required accuracy. For example, in spectroscopy, excited states have a finite lifetime. By the time-energy uncertainty principle, they do not have a definite energy, and, each time they decay, the energy they release is slightly different. The average energy of the outgoing photon has a peak at the theoretical energy of the state, but the distribution has a finite width called the natural line width. Fast decaying states have a broad line width, while slow decaying states have a narrow line width. The same line width effect also makes it difficult to specify the rest mass of unstable, fast decaying particles in particle physics. The faster the particle decays, the shorter its lifetime, the less certain is its mass, the larger the particle's width. In the context of signal processing, and in particular time, frequency analysis, uncertainty principles are referred to as the Gabor limit, after Dennis Gabor, or sometimes the Heisenberg-Gabor limit. The basic result, which follows from Benedict's theorem, below, is that a function cannot be both time-limited and band-limited. A function and its Fourier transform cannot both have bounded domain, see band-limited versus time-limited. Stated alternatively, one cannot simultaneously sharply localize a signal, function f, in both the time domain and frequency domain, f, its Fourier transform. When applied to filters, the result implies that one cannot achieve high temporal resolution and frequency resolution at the same time. A concrete example are the resolution issues of the short-time Fourier transform. If one uses a wide window, one achieves good frequency resolution at the cost of temporal resolution, while a narrow window has the opposite trade-off. Alternate theorems give more precise quantitative results, and, in time, frequency analysis, rather than interpreting the one-dimensional time and frequency domains separately, one instead interprets the limit as a lower limit on the support of a function in the two-dimensional time-frequency plane. In practice, the Gabor limit limits the simultaneous time-frequency resolution one can achieve without interference. It is possible to achieve higher resolution, but at the cost of different components of the signal interfering with each other. As a result, in order to analyze signals where the transients are important, the wavelet transform is often used instead of the Fourier. Werner Heisenberg formulated the uncertainty principle at Niels Bohr's Institute in Copenhagen, while working on the mathematical foundations of quantum mechanics. In 1925, following pioneering work with Hendrik Kramers, Heisenberg developed matrix mechanics, which replaced the ad hoc old quantum theory with modern quantum mechanics. The central premise was that the classical concept of motion does not fit at the quantum level, as electrons in an atom do not travel on sharply defined orbits. Rather, their motion is smeared out in a strange way. The Fourier transform of its time dependence only involves those frequencies that could be observed in the quantum jumps of their radiation. Heisenberg's paper did not admit any unobservable quantities, like the exact position of the electron in an orbit at any time. He only allowed the theorist to talk about the Fourier components of the motion. Since the Fourier components were not defined at the classical frequencies, they could not be used to construct an exact trajectory, so that the formalism could not answer certain overly precise questions about where the electron was or how fast it was going. According to one account, Heisenberg's paper marked a radical departure from previous attempts to solve atomic problems by making use of observable quantities only. My entire meager efforts go toward killing off and suitably replacing the concept of the orbital paths that one cannot observe, he wrote in a letter dated July 9, 1925. It was actually Einstein who first raised the problem to Heisenberg in 1926 upon their first real discussion. Einstein had invited Heisenberg to his home for a discussion of matrix mechanics upon its introduction. As Heisenberg describes the discussion, on the way home, he questioned me about my background, my studies with Sommerfeld. But on arrival, he at once began with a central question about the philosophical foundation of the new quantum mechanics. He pointed out to me that in my mathematical description the notion of electron path did not occur at all, but that in a cloud chamber the track of the electron can of course be observed directly. It seemed to him absurd to claim that there was indeed an electron path in the cloud chamber, but none in the interior of the atom. In this situation, of course, we, Heisenberg and Bohr, had many discussions, difficult discussions, because we all felt that the mathematical scheme of quantum or wave mechanics was already final. It could not be changed, and we would have to do all our calculations from this scheme. On the other hand, nobody knew how to represent in this scheme such a simple case as the path of an electron through a cloud chamber. In March 1926, working in Bohr's Institute, Heisenberg realized that the noncommutativity implies the uncertainty principle. This implication provided a clear physical interpretation for the noncommutativity, and it laid the foundation for what became known as the Copenhagen interpretation of quantum mechanics. Heisenberg showed that the commutation relation implies an uncertainty, or in Bohr's language a complementarity. Any two variables that do not commute cannot be measured simultaneously. The more precisely one is known, the less precisely the other can be known. Heisenberg wrote, "It can be expressed in its simplest form as follows: one can never know with perfect accuracy both of those two important factors which determine the movement of one of the smallest particles, its position and its velocity. It is impossible to determine accurately both the position and the direction and speed of a particle at the same instant. In his celebrated 1927 paper, Über den Anschaulichen Inhalt der Quantentheoretischen Kinematik und Mechanik, on the perceptual content of quantum theoretical kinematics and mechanics, Heisenberg established this expression as the minimum amount of unavoidable momentum disturbance caused by any position measurement, but he did not give a precise definition for the uncertainties delta x and delta p. Instead, he gave some plausible estimates in each case separately. In his Chicago lecture, he refined his principle, delta x delta p greater than or approximate h throughout the main body of his original 1927 paper, written in German. Heisenberg used the word Ungenauigkeit, indeterminacy, to describe the basic theoretical principle. Only in the endnote did he switch to the word Unsicherheit, uncertainty. When the English-language version of Heisenberg's textbook, The Physical Principles of the Quantum Theory, was published in 1930, however, the translation uncertainty was used, and it became the more commonly used term in the English language thereafter. Heisenberg's microscope. The principle is quite counterintuitive, so the early students of quantum theory had to be reassured that naive measurements to violate it were bound always to be unworkable. One way in which Heisenberg originally illustrated the intrinsic impossibility of violating the uncertainty principle is by utilizing the observer effect of an imaginary microscope as a measuring device. He imagines an experimenter trying to measure the position and momentum of an electron by shooting a photon at it. 49 to 50. Problem 1. If the photon has a short wavelength, and therefore a large momentum, the position can be measured accurately. But the photon scatters in a random direction, transferring a large and uncertain amount of momentum to the electron. If the photon has a long wavelength and low momentum, the collision does not disturb the electron's momentum very much, but the scattering will reveal its position only vaguely. Problem 2. If a large aperture is used for the microscope, the electron's location can be well resolved, see Rayleigh criterion, but by the principle of conservation of momentum, the transverse momentum of the incoming photon affects the electron's beamline momentum and hence, the new momentum of the electron resolves poorly. If a small aperture is used, the accuracy of both resolutions is the other way around. The combination of these trade-offs implies that no matter what photon wavelength and aperture size are used, the product of the uncertainty in measured position and measured momentum is greater than or equal to a lower limit, which is, up to a small numerical factor, equal to Planck's constant. Heisenberg did not care to formulate the uncertainty principle as an exact limit, and preferred to use it instead as a heuristic quantitative statement, correct up to small numerical factors, which makes the radically new noncommutativity of quantum mechanics inevitable. The Copenhagen interpretation of quantum mechanics and Heisenberg's uncertainty principle were, in fact, seen as twin targets by detractors who believed in an underlying determinism and realism. According to the Copenhagen interpretation of quantum mechanics, there is no fundamental reality that the quantum state describes, just a prescription for calculating experimental results. There is no way to say what the state of a system fundamentally is, only what the result of observations might be. Albert Einstein believed that randomness is a reflection of our ignorance of some fundamental property of reality, while Niels Bohr believed that the probability distributions are fundamental and irreducible, and depend on which measurements we choose to perform. Einstein and Bohr debated the uncertainty principle for many years. The ideal of the detached observer Wolfgang Pauli called Einstein's fundamental objection to the uncertainty principle the ideal of the detached observer, phrase translated from the German like the moon has a definite position. Einstein said to me last winter, whether or not we look at the moon, the same must also hold for the atomic objects, as there is no sharp distinction possible between these and macroscopic objects. Observation cannot create an element of reality like a position. There must be something contained in the complete description of physical reality which corresponds to the possibility of observing a position, already before the observation has been actually made. I hope that I quoted Einstein correctly. It is always difficult to quote somebody out of memory with whom one does not agree. It is precisely this kind of postulate which I call the ideal of the detached observer. Letter from Pauli to Niels Bohr, February 15, 1955. Einstein slit. The first of Einstein's thought experiments challenging the uncertainty principle went as follows. Consider a particle passing through a slit of width d. The slit introduces an uncertainty in momentum of approximately h/d because the particle passes through the wall. But let us determine the momentum of the particle by measuring the recoil of the wall. In doing so, we find the momentum of the particle to arbitrary accuracy by conservation of momentum. Bohr's response was that the wall is quantum mechanical as well, and that to measure the recoil to accuracy delta p, the momentum of the wall must be known to this accuracy before the particle passes through. This introduces an uncertainty in the position of the wall and therefore the position of the slit equal to h/delta p, and if the wall's momentum is known precisely enough to measure the recoil, the slit's position is uncertain enough to disallow a position measurement. A similar analysis with particles diffracting through multiple slits is given by Richard Feynman. Einstein's box. Bohr was present when Einstein proposed the thought experiment which has become known as Einstein's box. Einstein argued that Heisenberg's uncertainty equation implied that the uncertainty in time was related to the uncertainty in energy, the product of the two being related to Planck's constant. Consider, he said, an ideal box, lined with mirrors so that it can contain light indefinitely. The box could be weighed before a clockwork mechanism opened an ideal shutter at a chosen instant to allow one single photon to escape. We now know, explained Einstein, precisely the time at which the photon left the box. Now, weigh the box again. The change of mass tells the energy of the emitted light. In this manner, said Einstein, one could measure the energy emitted and the time it was released with any desired precision, in contradiction to the uncertainty principle. Bohr spent a sleepless night considering this argument and eventually realized that it was flawed. He pointed out that if the box were to be weighed, say by a spring and a pointer on a scale, since the box must move vertically with a change in its weight, there will be uncertainty in its vertical velocity, and therefore an uncertainty in its height above the table. Furthermore, the uncertainty about the elevation above the Earth's surface will result in an uncertainty in the rate of the clock, because of Einstein's own theory of gravity's effect on time. Through this chain of uncertainties, Bohr showed that Einstein's light box experiment could not simultaneously measure exactly both the energy of the photon and the time of its escape. EPR paradox for entangled particles. Main article, EPR paradox. Bohr was compelled to modify his understanding of the uncertainty principle after another thought experiment by Einstein. In 1935, Einstein, Podolsky, and Rosen published an analysis of widely separated entangled particles, EPR paradox. Measuring one particle, Einstein realized, would alter the probability distribution of the other, yet here the other particle could not possibly be disturbed. This example led Bohr to revise his understanding of the principle, concluding that the uncertainty was not caused by a direct interaction, but Einstein came to much more far-reaching conclusions from the same thought experiment. He believed the natural basic assumption that a complete description of reality would have to predict the results of experiments from locally changing deterministic quantities and therefore would have to include more information than the maximum possible allowed by the uncertainty principle. In 1964, John Stuart Bell showed that this assumption can be falsified, since it would imply a certain inequality between the probabilities of different experiments. Experimental results confirm the predictions of quantum mechanics, ruling out Einstein's basic assumption that led him to the suggestion of his hidden variables. These hidden variables may be hidden because of an illusion that occurs during observations of objects that are too large or too small. This illusion can be likened to rotating fan blades that seem to pop in and out of existence at different locations, and sometimes seem to be in the same place at the same time when observed. This same illusion manifests itself in the observation of subatomic particles. Both the fan blades and the subatomic particles are moving so fast that the illusion is seen by the observer. Therefore, it is possible that there would be predictability of the subatomic particle's behavior and characteristics to a recording device capable of very high-speed tracking, Ironically, this fact is one of the best pieces of evidence supporting Karl Popper's philosophy of invalidation of a theory by falsification experiments. That is to say, here Einstein's basic assumption became falsified by experiments based on Bell's inequalities, while it is possible to assume that quantum mechanical predictions are due to non-local, hidden variables, and in fact David Bohm invented such a formulation, this resolution is not satisfactory to the vast majority of physicists. The question of whether a random outcome is predetermined by a non-local theory can be philosophical, and it can be potentially intractable. If the hidden variables were not constrained, they could just be a list of random digits that are used to produce the measurement outcomes. To make it sensible, the assumption of non-local hidden variables is sometimes augmented by a second assumption, that the size of the observable universe puts a limit on the computations that these variables can do. A non-local theory of this sort predicts that a quantum computer would encounter fundamental obstacles when attempting to factor numbers of approximately 10,000 digits or more, a potentially achievable task in quantum mechanics. Popper's criticism. Main article. Popper's experiment. Karl Popper approached the problem of indeterminacy as a logician and metaphysical realist. He disagreed with the application of the uncertainty relations to individual particles rather than to ensembles of identically prepared particles, referring to them as statistical scatter relations. In this statistical interpretation, a particular measurement may be made to arbitrary precision without invalidating the quantum theory. This directly contrasts with the Copenhagen interpretation of quantum mechanics, which is non-deterministic but lacks local hidden variables. In 1934, Popper published Zur Kritik der Ungenauigkeitsrelation, Critique of the Uncertainty Relations, in Naturwissenschaften, and in the same year Logik der Forschung, translated and updated by the author as The Logic of Scientific Discovery in 1959, outlining his arguments for the statistical interpretation. In 1982, he further developed his theory in quantum theory and the schism in physics, writing, Heisenberg's formulae are, beyond all doubt, derivable statistical formulae of the quantum theory. But they have been habitually misinterpreted by those quantum theorists who said that these formulae can be interpreted as determining some upper limit to the precision of our measurements. Popper proposed an experiment to falsify the uncertainty relations, although he later withdrew his initial version after discussions with Weizsäcker, Heisenberg, and Einstein. This experiment may have influenced the formulation of the EPR experiment. Many worlds uncertainty. Main article. Many worlds interpretation. The many worlds interpretation, originally outlined by Hugh Everett III in 1957, is partly meant to reconcile the differences between Einstein's and Bohr's views by replacing Bohr's wave function collapse with an ensemble of deterministic and independent universes whose distribution is governed by wave functions and the Schrödinger equation. Thus, uncertainty in the many worlds interpretation follows from each observer within any universe having no knowledge of what goes on in the other universes. Free will. Some scientists, including Arthur Compton and Martin Heisenberg, have suggested that the uncertainty principle, or at least the general probabilistic nature of quantum mechanics, could be evidence for the two-stage model of free will. One critique, however, is that apart from the basic role of quantum mechanics as a foundation for chemistry, non-trivial biological mechanisms requiring quantum mechanics are unlikely, due to the rapid decoherence time of quantum systems at room temperature. Proponents of this theory commonly say that this decoherence is overcome by both screening and decoherence-free subspaces found in biological cells. Thermodynamics. There is reason to believe that violating the uncertainty principle also strongly implies the violation of the second law of thermodynamics, and this is known as the Gibbs paradox.